Good morning everyone. Yesterday we had a lecture on thermal energy storage system in renewable energy engineering, solar, wind and biomass energy systems. What we could cover is thermal energy storage, thermochemical energy storage and mechanical energy storage. So, today we are going to discuss about the collection and storage, which is nothing but solar pond and types of solar pond and advantages and applications. Okay. In solar ponds, what is the difference between normal and solar ponds? In normal ponds, we receive sunlight as a part of which is reflected at the surface and a part is absorbed and the remaining is transmitted to the bottom. So, this is what we have seen in normal non-concentrating collector. So, due to this, the lower pond gets heated up and the density decreases. As a result, the convection currents sets up in the pond. As a result, the heated water reaches the top layer and loses its heat by convection and evaporation with the atmosphere. Okay. In normal pond, when solar energy hits the bottom of the pond with three parts, right. One is reflection and another one is by absorption and another one is by transmittance, right. So, based on that, whatever the energy collected at the bottom of the pond, it takes the heat and gets heated up. Because density is low for the heated water, it tries to go above, and further the cold water which is there in the upper part of the pond comes down. So, this water further loses its energy with the atmosphere by evaporation or by convection. So, here if you want to store this heat whatever you gained at the bottom of the pond, there are certain technology which we need to do to trap the heat in the bottom of the pond. So, that is nothing but a solar pond. Solar pond is nothing but a artificially constructed pond in which significant temperature rises are caused to occur in the lower regions by preventing convection, right. So, what I supposed to do, because this energy is going waste to the atmosphere in terms of convection and evaporation, somehow I need to stop this convection in the bottom of the pond, so that it will not reach the surface of the pond and loses its heat with the atmosphere. So, to prevent this convection, a salt water is used in the pond, so that temperature gradient are reversed from the normal. So, if the density is high, then the hot water remains in the bottom of the pond only. So, that is where we reverse the thermal gradient and make the hot water to stay in the bottom of the pond only. So, this allows the use for collection and storage. So, we can collect the solar energy in the bottom of the pond, and by adding the salt water or salt into the bottom of the pond, we can stop the convection currents in the water and by and thereby convection and evaporation losses. So, solar ponds under ideal conditions be delivered at the temperature of 40 to 50 degree centigrade above normal. So, solar ponds combines the functions of heat collection with the long term storage and can provide the sufficient heat for the entire year. So, typically they are of 2 to 3 meters deep with a thick durable plastic liner laid at the bottom. Materials used for liner include LDPE, low density polyethylene, and high density polyethylene HPDE, woven polyester yarn, and hypalon reinforced with nylon mesh. And here some of the material can be black coated as well to trap higher solar radiation. And salts like magnesium chloride, sodium chloride, MgCl2, NaCl and NaNO3 sodium nitrate are dissolved in the water, and the concentration varying from 20 to 30% at the bottom to almost 0 at the top. The concentration at the top is very less, concentration at the bottom is 20 to 30%. The amount of salt required for this purpose is about 50 grams per meter squared per day, which is a large quantity when considered on an annual basis. It will vary depend on the capacity of the pond, and also since we are using salt, so the salt concentration of the water at the bottom of the solar pond is high. We need to also think about when it is being used for low temperature applications, it has to pass through the pipes, right. So, there may be a corrosion problems as well, but still based on the requirement and based on the storage system, salt can be used. So, the solar pond normally has 3 zones: surface convective zone, non-convective concentration gradient zone and lower convective zone. Surface convective zone is nothing but the topmost layer. This is of small thickness around 10 to 20 centimeter. Here the concentration is low and uniform concentration which is close to 0, and as well as fairly uniform temperature which is close to the ambient temperature. Then only there will not be any convection or evaporation losses. The temperature is almost ambient temperature, the concentration is 0 concentration, around 0 concentration. The non-convective zone, here it is thicker and occupies more than half of the depth of the pond. So, here both concentration and temperature varies or increases with depth, because we said concentration is 0 at the top layer to prevent the convection, and concentration is high at the bottom layer. This is top, which is nothing but surface convective zone, right, SCZ. So, this is last one is lower convective zone, lower convective zone. So, the temperature concentration increases. Here the temperature is ambient in the upper or SCZ, and the temperature is higher in the bottom lower convective zone. So, in the middle it increases with the depth. It serves principally as an insulating layer and reduces the heat losses in the upward direction. What we said, if you did not have put the salt layer in the lower convective zone, it starts, the convection current starts, right. So, basically this non-convective zone acts as an insulating layer because of high concentration and high temperature in the lower convective zone. So, some of the heat collection takes place in this zone as well, and basically it serves also as a part of thermal storage. Solar radiation enters through this layer, there is some collection also happens. Lower convective zone is nothing but this zone, comparable in thickness to the non-convective zone, and both the concentration and temperature are nearly constant and high as well. It serves the mainly heat collection as well as the storage, thermal storage medium. The lower convective zone is often referred as the storage zone or the bottom layer of the solar pond. So, this is nothing but daily mean temperature in the solar pond. So, if you see this is for almost 3 years it is taken. So, here if you see it is almost cyclic in nature with 1 or 2 months difference. The temperature in the lower convective zone, right, if it is well designed, well insulated and a large pond operating in India in the sense like medium solar radiation happens throughout the year. If the temperature in the lower convective zone fluctuates cyclically between a maximum of 85 to 95 degree in summer and minimum of 50 to 60 degree in the winter. The annual collection efficiency generally ranges between 15 to 25%, which is lower than the FPC, but still solar ponds are more cost effective and their cost per square meter is much less than that of the liquid FPC collectors. So, this comparison would be more effective if you have the large area of about 1000 meter squared or more. Working principle of solar pond. So, this is, if you see, this is the concentration, this is the depth of the solar pond which increases in the negative x direction. So, in the top concentration is C1, temperature is T1 and density is rho 1. So, this is obviously high in lower zone. and if you see the T1, which is the less temperature, the density is rho 1. For higher temperature you have density of rho 2. So, this is the curve which connects both, right, which is nothing but AB. Depth of the pond is L and having salts dissolved in the water. The concentration at top is C1, which is less than that at the bottom C2. The concentration gradient exists from the top to bottom. T1 rho 1 be the temperature and density of the top layer of the water indicated by A, right. So, there it is almost at the atmospheric temperature. T2 and rho 2 be the temperature and density of the bottom layer indicated by point B. So, if you want to write this ddx of rho should be greater than 0, right. The condition for lower layers remain denser than those above, right. If that condition is applicable, then ddx of rho should be greater than 0. So, in this case if you write rho as the function of C and T, concentration and temperature, how do you write? This is dou C of rho at constant T into ddx of C plus dou T of rho at constant concentration, which is multiplied by ddx of T, which is greater than 0. So, from this if you calculate dC dx, which is greater than of minus of dou T rho at C into ddx of T upon dou C of rho at constant temperature. Okay. So, this is nothing but minimum concentration required for maintaining a given temperature gradient, which is nothing but ddTx at a particular level in a solar pond. So, this is here the kinematic viscosity and thermal diffusivity and diffusivity of salt water is also added to give more stringent condition. Okay. Anyway, you can use this particular equation to calculate minimum concentration gradient required for maintaining a given temperature gradient at a particular level in a solar pond. So, types of solar pond: convective solar and non-convective solar pond. Convective solar pond, we do not make any special effort. Here it consists of pure water enclosed in a large bag that allows the convection but hinders the evaporation. The sun heats the water in the bag during a day. At night, hot water is pumped into large heat storage tank to minimize the heat loss. So, this is example is shallow solar pond. So, here we did not stop the convection by adding salt water or anything. So, normally we keep the large bag with the pure water. After taking the heat during the day, it will be shifted to large heat storage tank to minimize the losses. In a way, it can be used for further energy requirement. Non-convective solar pond is nothing but whatever we have seen just now. It consists of three distinct layers of brines, increasing concentration from top to bottom. So, membrane ponds are also available. Here in membrane ponds, we keep a plastic sheet between the layers to maintain the stability. Otherwise, there would be in interface layer. For example, this is SCZ, surface convective zone, this is NCZ, and then lower convective zone. So, this is based on the thermostratification, the layers become stable, but still we cannot expect them to be stable because of temperature gradient. So, for that purpose a transparent plastic sheet between the layers are kept to maintain the stability. Advantages wise, no need of separate collector for thermal storage. It can do both the operation, collection as well as storage. Low investment cost per installed collection area. The heat storage is massive, so energy can be extracted day and night. Source of baseland solar power, no batteries are needed for storage. Diffusive radiation is also fully used because it is a open area. very large surfaces can be built, thus large scale energy generation is possible, and expensive cleaning of large collector surfaces in dusty area is avoided, because if you are using FPC, so the top one is glass cover, right. If the if dirt gets accumulated, then you cannot expect the solar energy to be transmitted through the glass cover, but here also this dirt problem is there, right. If the dirty materials are gets filled with the upper zone of the solar pond, then there also must be problem, but comparatively compared with FPC, this may be lesser, because you can clean time to time, but cleaning is easy here in the solar pond than compared to FPC. It can store solar heat much more effectively than a body of water of same size. Applications: electric power generation, desalination process, domestic hot water production, and for space heating and cooling of buildings. Here we are seeing the electric power generation. In electric power generation unit, this is the one, right. So, from the boiler it goes to turbine. In the turbine, so it should be reverse, right. From the boiler it will go to turbine, from the turbine it goes to condenser, the working fluid, then after that it is pumped back to the evaporator, right. From the turbine, if it is connected to the generator, it produces the electricity. For the evaporator, you might require the hot water, right. So, the cold water is taken back and gets heated, it goes through the solar pond. So, here already you have a hot water, hot salt water, right. So, you take a cold water from the evaporator or boiler assembly and use the solar pond as the heat exchanger, and takes the heat from the hot water and goes back to the evaporator, where you again heat the working fluid. Okay. So, this condenser is connected to the cooling tower to provide the cooling water to take away heat from the working fluid. The application, commercial application, the first solar pond in India, about 6,000 meters squared, was built at Bhuj, which is in Gujarat. The project was sanctioned under the National Solar Pond Program by Ministry of Non-Conventional Energy Sources in 1987, completed in 1993 with the collaboration with TERI. This is the Energy and Resources Unit, Resources Institute, and the Gujarat Energy Development Agency and Gujarat Dairy Development Corporation Limited. So, this is the that solar pond taken from web source. The operational problems, the effect of rain. When light rain helps to maintain the salt concentration at lower level, because it dilutes the surface water and removes the need for flashing fresh water across the top. As I said earlier, there may be concentration change due to stratification, thermal stratification. So, in that case we then and there flash the fresh water to dilute the concentration at the top. If the light rain happens, this helps in that way naturally. If heavy rain happens, that penetrates the through the solar pond, it causes the increase in the thickness of the surface convective zone, which is about 40 to 50 meter. Wind induced waves, depth of the solar pond is 2 to 3 meter. In that the surface, so this is centimeter. Okay. The surface convective zone thickness is about 10 to 20 centimeter. Wave having amplitude of 2 centimeter can cause mixing up to the depth of 20 centimeter total surface convective zone, and the wave amplitude should not exceed this level, right. So, wave amplitude of 2 centimeter can cause mixing up to a depth of 20 centimeter. If the amplitude goes more than this, then this thickness would get disturbed. Okay. The technique to be used to remove this wind induced waves is float wind wave breakers on the surface of the pond. Then biological growth of algae is observed. This growth gives the water a greenish color and severely decreases the transmissivity of the solar radiation. The technique to prevent this is prevention by chemical treatment. Chlorination of water and addition of small amount of copper sulphate have been found to be very effective in to remove the or to suppress the growth of algae. Effect of bottom reflectivity. Increase in bottom reflectivity can lead to a deterioration of the pond performance. So, increase in reflectivity is quite high in the case of undissolved salt, leading to substantial deterioration in the performance. Horizontal temperature gradient can cause the disturbance, so which is created by salt solution removal and addition. So, what is the technique to be followed? Do it slowly. So, when you add the salt or remove the salt, so that should be done with the slow manner to avoid the horizontal temperature gradient. What we require is probably vertical temperature gradient only. So, in solar pond system, we have learnt about how the storage and collection happens in the single unit and various zones of the solar pond and what are all its advantages and what are all its operational problem. Further, you can refer this 3 reference material for in-depth understanding. Thank you.